Good morning everyone, and welcome to today's worked exam answer video. Today I am having a look at this calculations question where we've got two different calculations being asked as a part of the same question. Both of these calculations are first introduced in the amount of substance topic, which is taught in year 12, but of course, as I've said a number of times on these videos now, everything in year 12 is also relevant for those of you in year 13. So I would hope that if you are in your first year of the A-level that you have now done the amount of substance topic and you should be familiar with these ideas. I'm going to work through both of the questions as I always do. Any questions about anything that I say or write down, please do not hesitate to get in touch with me. So we're told the question is about two experiments on gases, and in the first experiment we are injecting a liquid into a sealed flask under vacuum, and when we do that, because of the temperature of the flask, the liquid vaporizes inside of the flask and becomes a gas, so that we can then work out the volume of gas inside the flask, and we've now got a pressure inside the flask, and we know how many milligrams of liquid Y we injected, and all of this is going to enable us to calculate the relative molecular mass of Y, and then we're given the gas constant. Now, when we're thinking about gases, one of the equations that we frequently will need to use is the ideal gas equation, which is PV equals nRT. And here we've got a temperature, we've got a volume, we've got a pressure, we've got a gas constant. So that should be triggering thoughts of, perhaps I need to do ideal gas here. However, they've also then merged in a second calculation whereby we're needing to work out the relative molecular mass. We've been given the mass, and the ideal gas equation allows us to work out the moles. So we're going to need to do two steps. One is rearrange the ideal gas equation to get moles equals and figure out what the moles are, then use moles and mass to get the MR. Now, with all of these sorts of questions, as you probably have seen by now, unit conversions are a big part of what you are required to do in these questions. So out of the four variables listed in this little table, 3 of them are going to need to be converted, and that is very standard for AQA questions of this nature, so I guess be prepared for that. So what I would always recommend that we do with any PV is nRT question is, first of all, write down PV is nRT, because there is in a lot of cases a mark for doing that, or for writing the rearranged version of that. In this case, we want to get moles, so it's going to be moles is equal to pressure times volume divided by the gas constant times temperature, and then we can sub those values in. Now, we're not ready to do that yet, and what I would suggest next is that we have a look at all the units that we're going to need to convert. So thankfully the gas constant is always given to us in the version that we'll need it to be. It's always going to be 8.31 joules per Kelvin per mole, and we're never going to have to do anything with that with regards to conversions. The only other value in the table that's been given to us in the right format is the temperature. Temperature here needs to be in Kelvin, and it is in Kelvin. It's 297 Kelvin, so we don't need to convert that one. If we were given it in degrees Celsius, we would want to be adding 273 to whatever the temperature we were given is in degrees. If you forget, the units are Kelvin for temperature. In the gas constant, we have got units of joules per Kelvin per mole, and the per Kelvin and Kelvin will cancel. So if that was in degrees, that wouldn't work. So you can use these units to prompt you to go, yes, need to have the temperature in Kelvin. So the ones that we're going to need to change, initially for my rearranged ideal gas equation, is I'm going to need to change the volume, and I'm going to need to change the pressure. And this is where remembering what units we need to have these values in is really important. So the volume inside the flask, every other calculation you would be converting it into decimeters cubed. For ideal gas, we're actually converting the volume into meters cubed. So from centimeters cubed to meters cubed, we would need to divide by a million, and that's because we're going through the decimeters cubed and then out to meters cubed. So that value there becomes, in meters cubed, 4.82 times 10 to the minus 4. And we've got to remember that it's meters cubed for the volume for ideal gas. If you are working out a volume, whereas we're working out the moles here, if you're asked to work out a volume, it will always come out in meters cubed, but again, they might then ask you to give that in any other units that they want, decimeters cubed, centimeters cubed. Sometimes they'll just leave you to write it in meters cubed. For pressure, they frequently give us the pressure in kilopascals. We want it to be in pascals, so we need to times our kilopascal value by 1,000. So here that's going to become 51,000 pascals. And now we're ready to sub those numbers in to our rearranged ideal gas equation. So pressure, 51,000 pascals, times my volume in meters cubed, 4.82 times 10 to the minus 4. And then we're going to divide that by the gas constant, 8.31, times by the temperature, 297 Kelvin. That is going to give me moles of 9.96 times 10 to the minus 3. Which, because I've done thousands probably of these calculations over the last 15, 16 years, maybe slightly longer, I know that that is within the realms of what I would expect for a mole value based on the numbers that we were given in the question. And that's the thing with calculations, the more you do, the more you'll be able to spot, oh, that number's very big, or oh, that number's very small. And even if we can't do that with the moles here, when we go on to work out the relative molecular mass now, if you're getting a relative molecular mass that's like 1, probably done something wrong. Likewise, if you get a relative molecular mass of 1,000, potentially we've done something wrong. So that's where you would then go back and check or think about, again, do I need to change some of the values that I was given? Have I forgotten to convert some of these units? And like I say, that will come with experience of doing more questions, but it's always a good thing to just ask yourself, is this answer looking like a viable answer given, you know, what we're trying to work out and the kind of information that we were given. So now we've got the moles, we want to work out the MR. So MR is worked out by doing mass divided by moles. Now moles are all ready to go from the calculation we've just done. Mass is not. The mass here has been given in milligrams. So again, we're going to need to convert that into grams, because mass, with the exception of time of flight calculations, will always be in grams. So we're going to divide the milligrams by 1,000, so that's going to give us 0.717 grams. And now I can just sub the mass and the moles into that equation. So 0.717 divided by 9.96 times 10 to the minus 3. And that gives me an MR value of 71.98788. So I'm going to write it to 988 for now, but whenever we're doing a calculation question, we have to consider how many significant figures to give our answer to. No, it hasn't told us to do that, but we need to consider it all the time. And in lots of cases, it will be comparing the number of significant figures of all of the values given in the question and using the least precise value. Now these are all given to 3 significant figures, so that would suggest my MR should also be to 3 significant figures. And it is going to be to 3 significant figures, but it's also going to be, perhaps more importantly, to 1 decimal place. When we're working out MR values using the AR values on our periodic table, they're all given to 1 dp, so MR values should always be given to 1 dp, which here matches the 3 significant figures. So if I'm going with 3 significant figures or 1 decimal place, that's going to give me an answer of 72.0. And there we go, 5 marks. So not horrendous. And if you show you're working out logically, and it does say show you're working, but please always show you're working, it's going to be easy for the examiner to award method marks if, for example, you forgot to convert one of these units, but then your method steps were all correct after that. You would pick up a number of the marks still. Okay? Any queries about any of that, as I've said, please get in touch, leave a comment on the video, or you can send me an email. In part B, we're doing a separate reaction on a gas. This time we're using a flask for a combustion reaction. So the method that we've been given is that we are going to remove all of the air from the flask. We're then going to add 0.0010 moles of 2,2,4-trimethyl pentane, which is an isomer of C8H18, to the flask. So we're combusting an alkane. We're adding 0.02 moles of oxygen to the flask, providing the spark to ensure we get complete combustion, and then we're cooling the mixture to the original temperature. Now, we've been given the equation, and importantly, we've been given the state symbols, because the question here is asking us to calculate the amount in moles of gas in the flask after the reaction. So the water will be liquid water at this point. Had we have not cooled the mixture down, the water would have been a gas, and we would have then had to have included the moles of gas in our calculation. Because it's a liquid here, because it's been cooled down, the only gases that we're going to include here are the moles of CO2 that are made, and whether we have any excess of either the alkane or the oxygen. So we're definitely going to need the CO2 moles. We may need some of the leftover moles of one of our reactant gases, and because we've been given the moles of both of those reactant gases, we can establish which of those is in excess and which of those is limiting. So I'm gonna rewrite out the equation underneath so I can make myself a very basic little table. So we've been told that we've got 0.0010 moles of the C8H18. So that there is 0.0010. And then we're told that we are adding to the flask 0.02 moles of oxygen. So that is then going to go there. Now, the ratio of the alkane to the oxygen is 1 to 12.5. So I need to figure out whether all of the oxygen is going to be reacted or whether all of the alkane is going to be reacted. So there's 2 ways that we can figure out which is in excess. We can take our moles of alkane, so 0.0010, times that by 12.5, and see how many moles that gives us. That gives me 0.0125. Therefore, we have got more oxygen than we're going to need to fully react with all of the alkane, and therefore the oxygen is in excess, the alkane is the limiting reagent. The other way we can do it is the reverse way round. So we can take the moles of the oxygen and we can divide that by 12.5, and then we can see that we get 1.6 times 10 to the minus 3, where this is 1 times 10 to the minus 3. So to react all of the oxygen away, we would need more moles of the alkane than we have, which again shows us that the alkane is the limiting reagent. Why is that important? 2 reasons. First of all, we always use the limiting reagent when we're then figuring out the moles of anything else in the equation that we've made. And 2, we're going to have to figure out how much excess oxygen is left over. So we are going to use up all of the 0.0010 moles of the alkane. So we're going to have none of that left over contributing to the final amount of moles. We're going to lose 0.0125 moles of the oxygen, because that is in the ratio of 1 to 12.5. So we can figure out how much of that is left over, which is 7.5 times 10 to the minus 3. We don't have any moles of CO2 originally, but we are going to make, in a 1:8 ratio with the alkane, 0.0080 moles of CO2. And as I said, we don't need to look at the water here because the water here is a liquid, and we're asked about the moles of gas in the flask after the reaction, and the water here is liquid water, not water vapour, so we can completely ignore the 9 waters that we have here. Therefore, to work out the total amount in moles of gas in the flask after the reaction, I'm going to be adding the 7.5 times 10 to the minus 3 to the 0.008 for the moles of CO2, and that gives me 0.0155 moles of gas. So we did 7.5 times 10 to the minus 3, add 0.0080. And that would be the moles of gas in the flask after the reaction. So we didn't have any excess there, but we did need to include the excess moles of the oxygen there. And I guess where some people may go wrong here is they may forget that we need to figure out which of the reactants is in excess, and then also importantly figure out how much excess we had, and add the excess of the reactant to whatever moles of gas that we've made. Hopefully that's been useful, guys. Hit me up in the comments if there's anything you want me to explain further, or you can send me an email to missgtutoringandresources@outlook.com. Thank you so much for watching, guys. Have a fab day.